For bucket 2 right here, the mass is going to be 3.63 kilograms. The radius is going to be roughly 0.71 meters. And for bucket 2 right here, the velocity is going to be equal to square root of the radius times gravity. And so that's going to be equal to square root of 6.97. And so that's going to come out to roughly 2.64 meters per second. That's the minimum speed in order to keep the water in the bucket. Okay, and now to find the actual speed in which the bucket's traveled, we're going to be using this equation, V equals 2 pi r, where r is still the radius, and then t is the time of the period, which is the amount of time it takes for the bucket to do a full loop. And then for bucket 1, if we plug in all of our information here, which is the same as with the previous one, we find that the actual speed observed was 2.35 meters per second, which is slightly larger than the expected result of 1.87, but that's to be a little expected because obviously when you're spinning the bucket, you're not going to not all the force is going to be perfectly transferred, and so it's going to be a little bigger than calculated. And you can see the same over here for bucket 2, in which after plugging in our information with a period of 1.3 seconds, we find that the speed observed was 3.437 meters per second, which is slightly more than the previously calculated one. And so the speed you find using this equation right here is going to be a little less than the one you observe using this one right here, just because of the fact you're not going to go as slow as you can because you're trying not to have the water falling. So to begin with, we're going to use this equation, which is given to us: m times g equals m times v squared over r, where m is equal to the mass of the bucket in water, g is gravity, 9.8, v is the velocity, and r is the radius of the circular path that the bucket travels on. And then we're going to take all the information we have for our buckets. This is bucket 1 with a mass of 0.1814 kilograms, and the radius of the path it travels in is 0.3556 meters. And then with bucket 2, the mass is going to be 3.63 kilograms, and the radius of the circular path it travels in is going to be 0.39 meters. So, knowing we have this equation and we want to find the speed at which the bucket has to travel in, we're going to move around some of the different factors we have in order to get this equation. V equals square root radius times gravity. And using this equation, we can plug in the information that we have available in order to find the value of V. So this is what we have for bucket 1, where V equals square root of 0.36 times 9.8, which is equal to square root 3.48, which is roughly equal to 1.87 meters per second for bucket 1 being the minimum speed it needs to travel in order for the water not to fall out. Then, with bucket 2, V equals square root 0.39 times 9.8 equals square root 3.8171, which is roughly equivalent to 1.95 meters per second in order for the water to stay in the bucket for bucket 2. And now that we have our predictions for the minimum speed needed in order to keep the water in the bucket, we can test to see if the real result is accurate.
Alright, so to find the velocity at the top of the loop, we will use this equation, which is mg equals mv squared divided by r. Then once we simplify, we get the velocity equals the square root of gravity times the radius, and then we input the gravity, which is 9.8, and the radius, which is 0.24 meters, which gives us that the velocity needed to make the circle from the top to the bottom is 1.53 meters per second squared. Then knowing that velocity, you can find the acceleration inside of the circle, which is 0.29 meters per second squared. And because the acceleration is the same no matter where the circle is, we don't have to solve for that anymore. Now we'll find the max height needed to make the loop. So for that, I know that it's 2.5 times the radius, so then we input the radius, which is 0.24, then we multiply it by 2.5, giving us that the minimum height that we need to make the circle is 0.6 meters. Okay, so now we'll find the minimum velocity needed to enter the circle. For that, you'll get 1/2 times mass times velocity squared equals mg to radius plus 1/2 mvc squared. Vc is the velocity at the top of the loop. And then we just simplify. We know that the velocity at the top of the loop is square root gravity times radius, so then the square root and the squared power cancel out, and then we just simplify, dividing both sides by m, and then adding the same terms because gr are the same, so you add them, and then you just multiply by 2 to get v by itself, and then you square root, which gives you velocity equals 5 times gravity times radius, all getting square rooted. Then we plug in what we know, and we get that the minimum velocity needed is 3.43 meters per second squared. And I got all this from a YouTube video that will be down in the link below.